Hello, I'm sorry. Can you hear me?
Yes, yes. Sorry, I forgot to unmute. I just put
Okay, thank you.
Sorry.
So, what is its isometry? Its isometry group is just the orthogonal group of the previous diagonal form, divided out by the center, which is plus or minus the identity. Which means that actually any isometry comes from a linear map, a bounded linear map that preserves the quadratic form. Okay, and maybe I can explain this thing. Okay, if you look at the model, you see that the group of automorphisms of the quadratic form map to point to the number one. It is positive on the plane. The action is positive on the plane. So you only have to consider cell level of 1 point. And if you say this point, it's not very difficult to show that its orthogonal is isomorphic to Hilbert plates, and you have to understand the isometries of Hilbert plates, and they are all linear and come from orthogonal transformation. So the isometry group is this one.
So this group is not finitely generated, right?
Not at all.
Its finite generated subgroups are hyperbolic, or just to understand if you take a finitely generated subgroup of this group, would it be hyperbolic or not?
No, there is Z squares.
If, for example, it can be orthogonal. I mean, it can be unitary,
Yes.
but if you take a subgroup of different, which is finitely generated, and the action is proper on the hyperbolic space, then
Then it would
it
be
is
hyperbolic.
hyperbolic. Okay.
Thank you.
But actually, it is very large compared to a finitely generated group. It is a Lie group, but of infinite dimension. It is Banach Lie. So it means that it is a manifold modeled on some Banach space. Okay, and you can use the norm operator on this group, and it's not the good topology because it's very large. It is actually not separable, and there are very few compact sets. So we will not be interested in this topology, which is too fine for Python. And we want a smaller, more interesting topology. So we call this definition of what is Polish group, which is topological group, which is both separable and completely metrizable. They are nice, I mean, for analysis because that's bare property. So we can do argument how they are used for metric spaces, which are separable. Okay, so let me show you a few examples. The first example comes from locally compact groups, which are seven mutable, like lead groups or these groups, which are mutable. So algebraic groups of local fields or morphisms of finite of locally finite groups. Okay, but you have some other groups that are more mysterious or less valuable. For example, if you take a group of all the integrals, not necessarily finitely supported, but all permutations of integrals. Then equality group with boundwise convergence topology, and with that topology, it is equality. Okay. And another example, if you take the orthogonal group of Hilbert plates and you handle it with a stronger group topology are the same group, then you get another kind of Polish group. Okay, so let me introduce the Polish topology on the isometry group of the infinite-dimensional hyperbolic space. The construction is actually quite generic. If you take a metric space X, which is complete and separable, then its isometric group G has the Polish topology. With the one-polarized convergence topology. And maybe I can just write what this means. So at the end, it will be Polish, so topology is given by a convergence of sequences, and the sequence G and convergence G if and only if any One indicator and any epsilon. There is one and another and the distance between G and X I and G X I is epsilon. Okay, and I plan that methodology is a pollution. Okay, let's give a sketch of proof from. X is a verbal, so there is a dense sequence on X and we want to build a metric to get a Polish topology. So for any element G and H, we use this function and the same thing for the inverse. And taking, for example, a series and to the end, we construct a metric which gives the contrast convergence topology, and with that topology, we show that it is Polish, it is separable, and so we have Polish topology. And in particular, for the elementary group of Hilbert space or for the infinite-dimensional hyperbolic space, we get Polish topology. If you are used to operator algebra, it comes from a smooth operator topology. It is the same. Okay, so I have these two groups. I don't know Hilbert space, I don't know infinite-dimensional hyperbolic space, and I want to compare them. I want to show that somehow they are brothers. They are very good the same, but
So Bruno, first a question on this.
Yeah.
So in some sense, this is the weakest possible topology you could consider. That's huge open sets. Could it be that they are Polish for different topologies? Is there an argument why this is the best one?
okay, there is an argument it is the best one because it is the unique one, and we will show that in a few minutes. Okay, that is an interesting question. I will explain a bit why it is a unique one. Okay. So somehow we have two spaces, Hilbert space, hyperbolic space. They have a curvature of 0 or -1, both of in dimension, very homogeneous. And we want to compare the identity. First, as topological space, they are the same. There is no difference between both of them. If you are a topologist, you can see why those are very generic explanation, but I want to show in this particular case why it is the case. Okay. This two group can be right as a product of the space times the stabilizer of the point. Because the action is continuity. So each is a product as a topological space of the space, Hilbert space or hyperbolic space, and the stabilizer of point, which is in both cases is orthogonal. So if you put just a product here, and you take product topology, this book is isometry, is isomorphic, the product, and it is the same thing for T1. But as algebraic structures are completely different because for the isometry group of the Hilbert space, we have a similar product, and here there is no normal closed circle. We can show that it is topolohically simple. So they are topolohically the same, but algebraically completely different. One is simple as topological group, and the other is not. Okay. And the proof that they are the same is that you can split as a topological space as a product, orthogonal and the space. And the Hilbert space and the hyperbolic space are isomorphic. The Okay, so now a few objectives. We want to study in parallel groups and answer the question how one should consider them as Lie groups, I mean subgroups of children or are something larger like symmetric group of injectors. And can one understand their topological dynamics? And here by topological dynamics, I mean axon impact sets. Okay, I start with topological properties. Something which does not appear in finite dimension is the so-called automatic continuity property. The group has this property if any homomorphism to a several equal space is continuous. Of course, we have to add separability here because if you map to any space and you want that to be continuous, it will be too large. So you have to take the group with discrete topology. We have homomorphisms, and if it is continuous, the value will be discrete. It won't be interesting. But it's only interesting if you restrict to separable groups. Okay. Let's start with a few examples. This property is rare in the locally compact world. For example, simple group, the real with the addition and the usual topology does not have this property. Okay. Why? Okay. The group R is isomorphic as a group R2. Because if you take an R, if you consider R as a Q vector space, there is basis which is uncuttable. And similarly for R2. So you map one base to another one, and you get a map, and for sure it is not continuous. Okay. Now another example. SNC does not have this property. For example, if you take an automorphisms of the field C, it's not continuous. We know that the unique non-trivial of continuous homomorphisms of the complex number is the conjugation, but there are other automorphisms that are not continuous. And if you take one and you apply it coordinate by coordinate, you get isomorphisms of length which are not continuous. Okay, but for very large group, like the group of all bijections of CD integers, one has this property. Okay. What about the isometric group of hyperbolic space and the Hilbert set? Actually, both of them have this automatic continuity property. And the proof is very similar. We rely on one property, which is called the Steinhaus property. For the political group G, it has the Steinhaus property if there is a K, which is an integer and which is fixed one for all, such that each time you find a sigma subset, then W to the K contains the number. And maybe I have to say what it is. Sigma into that set. You can cover G with cantabile translates of W. Maybe I should say why this property implies schematic continuity. From a new group, which is dynamic, to another edge, which is the problem. And you want to show that this map is continuous. So we take O, open neighborhood of the identity. And your goal is to show that the perimeter of O is open. And I claim that this subspace of G is sigma simulated. Why? Because in H, you can cover H by contamination translate of O, because H is the variable. Okay, so if you take the frame H, since the image of G contained in H, you have that this one is sigma symbolic. So you know that the perimeter of power K contains an open subset. It's not exactly what you wanted, but we are almost done. Because if you start with not U, O, but some U, such that U, the power K, is contained in O, you can do the same thing with U, and you get that image of U, the power K contains an open set, and that's one image of O contains an open set, and you have an okay, so we just have to prove this Steiner property. And we will rely to this theorem due to the Schumpeter that the orthogonal group O from H has the Steiner property. And it means that Steiner of the point either for the Hilbert space or the hyperbolic space is Steinhaus, and playing with three stabilizers, we can prove that the group is also Steinhaus. Okay, so the real life with the stabilizer of the point is always the orthogonal group, and it has Steinhaus property. Okay. Okay. Maybe I won't enter into the detail. We use three stabilizers. Okay. But let me state something. If you have the automatic continuity property and you want to compare different Polish topologies, this means that this one is the finest possible. Okay. So in somehow the topology that I introduced is a maximal one. And now I want to state that this topology is actually a minimum one. Okay, for these two groups, the Polish topology that I introduced are minimal. There is no coarser group topology at all, even non-Polish. Okay, I won't go into detail, but the idea is prove that the variable of point at infinity are closed subgroup and then use dynamics that I will speak later. Okay, so if you combine the two results, you get that the Polish topologies and both group are actually unique outdoor separable topology. So it's the best one. Okay, that was about topology. Now let's go to topological dynamics. Okay, and I remind you that I want to understand action, continuous actions in compact spaces, in what I call topological dynamics. Okay, first we have to construct compact spaces on which the group act. Okay, a priori, we are in infinite dimensions, there is where may I find compact spaces. Okay, if you are used to finite dimensional Lie groups, often you have some symmetric space, and you can classify them by adding a boundary at infinity, and so you get a compact space. Okay, here I can consider either the Hilbert space or the hyperbolic space. It is the non-positive vector space, and I can add a boundary at infinity, but for both spaces, we get Hilbert spheres. And Hilbert spheres are not compact. The boundary is actually the projective code in rest. Okay, it's really Hilbert spheres. And in particular, the spheres are not compact. It is not a good way to do that. In finite dimensional world, often we use what is called the Bartholin boundary, which is G over P, G is our group, and G is cellular to 1 at infinity. And it's not in fact because it is exactly in the Hilbert sphere. So we have to find something else. And I will introduce a few other models of the hyperbolic space. So in blue, you have the hyperbolic model. Here you have the Klein model, which is just an infinite dimensional board and geodesic are straight line. And go from one to the other and take the line 0 to a point in the hyperbolic field, and the intersection with the space at altitude 1 is exactly the point in the line model. Okay, and we have another model, which is Poincaré model. It is also a ball of infinite dimension, and here geodesic are circle. Okay, I want to change the model before I talk about the hyperboloid one. And here I explain exactly how I do that. I want to show that the infinite dimensional hyperbolic space is the same thing as a sphere. I have a point if in the unit sphere, I take the point which is just above, adding P0, which is first coordinate, I get a point, and now I draw a straight line with this point and 0. Its intersection with the hyperboloid is symmetry. So there is a correspondence between unit disk and that of X. If you want the explicit formula, we can construct in one activity. Okay. And here, geodesic are straight line, and here are the okay. And what is the advantage to do that on the unit ball with maybe its boundary? We have the weak topology. Okay, in the first case, we have the weak topology, which is the coarser topology generated by open half spaces. Okay. And for this topology, the closure of the unit ball is a compact space. So, nice. In the hyperboloid model, H infinity, topology corresponding topology is the one generated by connecting components of the geodesic submanifold of dimension 1.
If I can interrupt you a second, there's a question from the audience about conformal structures. Do you also consider the conformal structure on the sphere, on the boundary of the ball?
It does not appear here, but yes, the isometric group can be considered as a Möbius group of this conformal structure at infinity.
So just as in the classical
Exactly.
two-dimensional case.
Yeah. Okay. So with this correspondence, we have a compact space, D-bar, which is the unit closed wall results topology, and we have a correspondence with the hyperbolic model and the unit sphere at infinity. Okay, and one remark which is very different with what happened in finite dimension. In T3 composition, sphere at infinity and the inner space, the large part is at infinity. Okay? The unit sphere at infinity is called meager. What is inside is meager. And maybe I have to explain that. The unit ball in the error space, and I take the ball of reduce, let's say, 1 minus 1 over n. It is the ball, and I take the draw ball. Okay? It is convex, so it is also closed for the root topology. And I claim it is there's an empty interior because if you take a sequence of points, for example, make let's say something which is lambda I, 2I, this is 1 minus EI is the unit base of the error space, and I multiply by a number which is larger than 1 minus 1 over n. So it is outside the ball. And this sequence for the weak topology converges to 0. So this ball has empty interior. And the unit ball, the open one, is the union of space. So it is a countable union of closed subspace of empty interior, which is a meager set. Okay, so the large part is really at infinity. So we first constructed one compact space, and maybe we will show that the group acts on this compact space. Now let me show you another construction of compact space, which holds from any metric space. If I have a metric space XB, I want to consider pairs of points as functions. So for 3 points x, y, z, I consider this function by index yz of x, which is the difference of this kind of function to y and z at x. The important part, thanks to the triangle inequality, it's like it is finite and closed interval. Okay. Now I can construct this space x2, which is the product of all pairs yz differences of this interval. That is a product of compact space, which is a compact space for product topology. And I get naturally a way to compactify x to a point small x in our metric space, we map it to this sequence indexed by Y and Z. Okay, so I identify a point in a metric space with all the difference of distance whereas Y is. Okay, so I have the backspace, and we have a very natural action in space by shifting of coordinates. Okay. If I have an element of the isometric group, what happens when I multiply x by j? With this formula, in fact, to preserve the distance, we see that it is exactly 5 g minus 1 y, g minus 1 z of x. So it is really the action by permutation on the coordinates. And since we use the product topology, the action is continuous. Okay. One more compact space, and we'll see that they are all related actually. Let's see in Duchesne, which means comparative code. You take where x are, where x is an element of unit ball, closed unit ball, and R is some real number between 0 and 1, such that R is larger or equal to the norm of x. Okay, I'm just drawing here where we are inside the code. Okay, and you have mapped the fourth coordinate just by projection. So now, what is the link between all two spaces? Is the following theorem. We can explicitly show that the overall compactification of the infinite hyperbolic space is Duchesne. Okay, so it's really a space that we can understand completely. And moreover, when we consider the projection from the overall compactification to the unit ball, it is continuous, and what is important, it is G equivariant. Okay, actually, here we have in the previous world, we have the composition in some product space, but it's just topological. There is no reason why the action is on the first coordinate and on the second one. But here we prove that the projection mass is the G map.
What is G? Your group of isomorphs? What is
Yes,
G?
yes, exactly. G is geometry.
Is there a way of writing the action on the frustum? Or it's just some abstract homeomorphism?
No, you can, okay. Because of the theorem, you see that the action is you act on the first coordinate. Here it is the Klein model, okay? And you have the action on R depends on the point X. It is not a product action, but you can write an explicit formula which tell you what is the image of R, and it depends on X.
So it's some co-cycle which has a meaning? No.
Not obvious. Maybe it has a geometric meaning, but I don't know. Okay, so as a corollary, we see that the unit closed model is a compact space and with a continuous G action. So here we have the first example of an action, continuous action in compact space. Maybe I will skip what happened for the Hilbert space. Actually, we have something very, very similar at the beginning. The compactification is still Duchesne, but the action is completely weird. And when you project, you don't get a continuous map. which is G equivalent. And so you don't get the continuous action in compact space, and somehow a bad reason is the fact that this group of isometry X is extremely minimal, which means that each time you have an action in compact space, there's a fixed point. Okay. Partly it explains why above we can do the same instruction as for the hyperbolic space. Okay. Now can you go past? I want to say a few words about what is the Platinum boundary. We have seen one action on compact space. Now, there could be many actions on compact spaces, but there are some universal ones. And here I will speak about the Platinum boundaries. For any topological group, there is one compact space on which the group acts continuously with the following properties. The action is minimal. There is no closed invariant subspace, which is non-empty, and the action is strongly proximal, which means that all probability measures can be compacted through direct math with elements of the group. Okay, so there is for each topological group a universal space which is the so-called Platinum boundary. And if you understand this Platinum boundary, you will understand any other strongly proximal action because it is a quotient of this Platinum boundary. Okay, maybe some examples that you know. If you take the symmetrical B group, which is not compact, or the isometry group of symmetric space of compact type, for example, SLM the space G over P, where P is the minimal parabolic, is the Platinum boundary of T. And for the isometry group of Duchesne and hyperbolic space, it is exactly this closed uniform. I just want to say one more what people can but Steve is actually for interdimensional closed world, we have two forms. One which is inside, which is the hyperbolic side, and one which is the boundary at infinity. We have two orbits, and I told you that the last part is the sphere at infinity, and for a point at infinity, it's stabilizer from it can be returned. When you stabilize the point at infinity, you stabilize all spheres. But you can move one more sphere to more sphere, so there is a half factor. And each power sphere is actually with the length distance Hilbert space. And there is only two groups H. This one is extremely minimal. And this one is a minimal. So this group is the minimum, and it is the point so that the first number is this way. The general stabilizer of the point is a minimum, is not sufficient.
It should be the boundary. It should not contain the inside. Right.
It contains inside because the inside is the closure of the outside.
Ah, yes.
Okay. So, what is the light clock? One or the
No, you still have 1 minute. 2 minutes.
just say one word about a universal element. So I can construct, I can send in all action on backspace, and maybe I want to reduce to minimal one. And among the minimal compact action, there is really one, which is called the universal minimum flow. And I want to say that one can completely describe this universal minimum flow for the identical group of the hyperbolic space. Given this expression, I need just not to quotient of universal definition, and a fiber is given by universal multiple of R. Okay, so we can describe it completely, and it's come once again because of the fact that stabilizer of point extremity is this secondary group. Here it is extremely minimal, but if it is not extremely minimal, it's just minimal. So we have to add a bit universal minimal group. And I stop it. Thank you.
Thank you very much. Questions or comments or remarks? Please.
Yeah.
Could you say a few words about this component that you said were generated by half spaces? Is that useful topology in terms of half spaces?
Yes. So it's topology which is bigger than you want distance, and the main point is when you add the boundary at quantity, it becomes complex space. Is crucial about it.
So you mean half spaces like dimension one, like
Take a two-dimension one complex space, and take okay, so it's complement component and it's
and for example in the complex state that we might not have
you're right. You do not, okay, for the complex case, and you don't have codimension one, real codimension, then so you have to, yes, you have problems. Because such a space is not a complex space.
But you really need the property that separates into for example, our spheres also separate into components that coordination one.
But okay, you can do the same topology for the complex spectrum, but it's definitely
and it will bring also a compactability.
There is a question, I guess, from the audience. So it's from the from Zoom. No,
Yes, it's. Can I ask a question?
please, please.
So my question was, I was wondering if you had nice embeddings of the space of projective measured laminations of a surface of genus G greater than 2 into the sphere at infinity of this hyperbolic space, and which preserves some structure like the maybe quasi-isometric for the intersection form. Does my question make sense?
I don't think it is the path from lamination to the boundary at infinity. Maybe it makes sense, but I didn't see it right now.
So maybe I'll add some context of. So the reason why I'm asking this question is because Bonaon gave a model of projective measured laminations or measured laminations inside the space of geodesic currents as the zero locus for the intersection form on geodesic currents. And this intersection form behaves a lot like a hyperbolic metric. So he makes an analogy with infinite dimensional hyperbolic space. Of course, in this case, geodesic currents has much more, and it has more signature in some sense. But if we just restrict to projective measured laminations, I was wondering if there were ways to naturally embed this in your space.
We look at the paper of Bonaon to try to understand that.
So classically, you enumerate the countably many, say, closed curves on the surface, and then that will be a basis for a space, and you look at the intersection, while the integral of the lamination along that curve. Just I don't see any summability condition here. Why would this be a Hilbert? It seems like it gives probably a much bigger space than the Hilbert space, which also happens to have a nice form. And perhaps, even though you get something bigger than Hilbert space, you will get the same isometries. One remark from here? Question? Yes, please.
No, do you have automatic continuity for the complex scales?
I think so.
And
it is not written.
okay. And for example, I mean, the first thing I saw that would be problematic is maybe the structure of the stabilizer of a point.
But it is the internal group of the synthetic. So we have the same result as you.
Okay. So you would expect that follows the same path.
Yeah.
I had perhaps a remark concerning Anna's question. So you told us about the Steinhaus property. So it seems this implies that the group is very far from being finitely generated, in the sense that if you take any finitely generating set S, then S to the K is the whole group.
S to the K is what?
Is the whole group. The growth series stops at distance K. Right? Because being finitely generated, being a generating set is sigma synthetic. So I was wondering, is this actually equivalent? This property that the growth series is bounded, this is something that was studied by Bergman about 20 years ago, maybe a little bit less. That's related, yes. It's bounded generation, in the sense that for every S, if S is a generating set, then S to the K, so words of length K, cover the whole group. There's an old result by Ore that this holds for the set of permutations of a countable set. And then this was sort of generalized by Bergman. I think it's called the Bergman property.
Excuse me, it seems there is a next course now. Maybe we can thank the speaker again.
I think, yes, we should. And let Anna.
Our next meeting is on March 12th. It's Tuesday, and we'll have a meeting on random walkers and groups. I suggest we continue maybe discussion. We can move to the kitchen to have coffee.
Just a last question. I'm sorry. Will we have access to the recordings?
Yes, the recordings are on the cloud, and they'll be linked from the website of the conference, hopefully tomorrow, or at worst after tomorrow. We'll try to do it tomorrow, as soon as Zoom makes them available to us.
Thank you very much. Bye.
Bye, everybody.